Hey everyone, Morgan here. So we're looking at page 2 now of the acids and bases outline for Honors Chem. And we're going to talk about some different definitions or some different models that describe acids and bases. Svante Arrhenius, one of the very first Nobel Prize winners in chemistry, and the guy who came up with the complete idea, the theory behind ionization. In fact, a lot of people say he's really one of the inventors of physical chemistry. The Arrhenius Model came about in the late 1800s, and it is the model that is still mostly taught in middle schools, biology classes, etc., for an acid or a base. In this model, acids are H+ donors, or hydrogen ion donors, and bases are OH- donors, or hydroxide ion donors. Now, this is a great reaction to illustrate this. HCl is giving up its H+, NaOH is giving up its OH-, and that's forming water. Okay? Now, that covers maybe 80%, maybe even 90% of all acids and bases. Covers a lot of them. Now, doesn't cover all of them. So sometime in the early 1900s, Bronsted and Lowry, working independent of each other, came up with a theory that acids were proton donors and bases are proton acceptors. Now here's the thing. An H+ ion is just a proton. So the definition for acid didn't change. It's just said differently. We use a different word for it. Now, why didn't Arrhenius say that? Well, because when Arrhenius did this work, we didn't know what protons and electrons were. Okay, this was before their discovery. Now, the base has a different definition. Base is something that is negative or capable of accepting that positive charge. Okay? This is still a great reaction to illustrate it. HCl still gives off H+, and the OH- is capable of accepting that H+, that proton, to form the water. So in both of these cases, acid-base, acid-base. Okay. Now, this got us up to about 98-99% of all acids and bases. It was in the early 1930s that Gilbert Newton Lewis, working up at UC Berkeley, assigned one of his graduate students, a guy named Glenn Seaborg, to round out the theory and not require the presence of a hydrogen ion. Acids became electron pair acceptors, and bases electron pair donors. Now the thing is, this doesn't change any of these definitions. That's still an electron pair acceptor, that's an electron pair acceptor. We're just describing it differently. Okay? OH- is an electron pair donor. It's great. But what this definition did was it allowed us to include compounds like BCl3. Now, BCl3 is short of an octet. Okay? It's only got 6 valence electrons around it. It can take 2 more. And this NH3, ammonia, has a lone pair, which can be donated to that boron, making it a base and making BCl3 the acid. Okay? There's not a ton of compounds that need this definition, but important ones. Okay, so those are our models now of our different theories of acid-base definitions. Okay, so on the last page we started to touch on the difference between strong and weak acids. We need to know the 6 strong acids. HCl, HBr, HI, H2SO4, HClO4, and HNO3. Hickel, Hibber, and Hi, the friendly acid, H2SO4, HClO4, HNO3. Do not memorize the weak acids. If you know this list, any other acid is automatically a weak acid. Okay. Now how about the strong bases? We don't have a list, we just say the metallic hydroxides. As long as they're soluble. We're not going to get into that so much, but there's one weird one, beryllium hydroxide, which really isn't soluble, so it doesn't associate. But take a metal, group 1, group 2, etc., throw hydroxide on it, that's a strong base. Okay, thanks for tuning in. This is Morgan, signing off.